This is the video for 7-3 day 2, second day on integration by parts, and today we'll start picking the U's and the DV's and give you some suggestions. This is the warm-up, so take a minute as you're taking notes, jot down the answers to these, pause the video right now, and then come back. Okay, so if you're back, you're checking answers to the warm-up. And as you can see, first one's just filling in that formula. Second one is taking a part with the suggestions of U and DV already given to you, and then putting them into the formula and working your antiderivative for natural log of 5x. Today, in 7-3 day 2, we're going to start picking the U's and the DV's to make this integration by parts happen as we get deeper into this subject. So as we work through here, you want to keep in mind a few things. All these are general guidelines. Guidelines are not 100% absolutes. So just like any other method, it doesn't always work for a given integral. So we have to have lots of methods, and this will add an additional one to try on integrals if direct antiderivatives and U substitution don't work. We might even need to blend some U substitution in. So in general, then we're going to get to really specific rules today, but in general, you want to choose a U that's part of that integrand whose derivative will be simpler than the actual expression of U. You also want to choose dv to be the more complicated part that can be easily integrated. So when you're choosing U, the general idea is to pick something so that the derivative is going to be simpler than the original U expression. And the opposite, you want to pick dv so that you have something that's more complicated, but something that's going to be easily integrated. And with some experience, that gets a little bit easier. We're also going to give you more specifics on when to pick different functions as your U. But there's no perfect method here. 99% of problems can be done with integration by parts using these guidelines, but you're going to come across a few that don't fit. So keep an open mind. So as we work through just this basic one, let's see if we can take that first rule of keep U, the idea that du needs to be simpler than U. So as we look through this, I sort of see two functions. I see that 2x in there, and that 2 could really go with either function. And then I see that e to the 4x, and one of them, when it becomes dv, will keep that dx, and one won't. So if 2x were my u, the x expression, that 2x expression will have a much simpler derivative than 2x. So I'm going to choose 2x as my u, and the rest of it then, the e to the 4x dx, will be my dv. I need everything from that integrand represented. Du then becomes 2 dx, a much simpler than 2x even. And my v then, when you do your antiderivative of e to the 4x, you're going to come up with 1/4 e to the 4x. If you need to see where that came from, go do some U substitution over on the side for a minute. So if we're trying to integrate e to the 4x dx, you can think of your u, different u here by the way, as 4x for substitution. So your du then is going to be 4 dx. So I need a 4 in there. To get that 4 in there in order to make that substitution, I'll need a 1/4 out front. And then when you integrate that, you can see where that 1/4 e to the 4x came from. So now that those are picked, now I need to go to the basic idea that as I try to evaluate this indefinite integral, I'm first going to come up with u times v. So as I combine those two, 2 times 1/4 is 1/2 x e to the 4x, subtract the integral of, and then this becomes our v du. So as we multiply the v and the du together, I'm going to come up with 1/2 e to the 4x dx. Now I want to keep working this because I can evaluate that inside integral, but I at least have the beginning part here. As I work this, I can pull that 1/2 out front, and then I'd still have that integral of e to the 4x, but here's the good news, I know what the integral of e to the 4x is. I just did it. It's 1/4 e to the 4x, and then we need to add our constant. So go back and look at what your dv had been to see why I knew that. So my final integral for this, or antiderivative value for that expression, 1/2 minus, this will become a 1/8, e to the 4x plus the constant, since there are many different functions that this could have had a different constant and still had that as its derivative. So when we look in there, we chose our u as 2x of all of that so that its derivative would be simpler than u itself. More specifically though, as you pick the u values, you might want some more general or more specific guidelines. So in general, when you pick this, you're going to go through something called LIATE, and you can pronounce that however you'd like, but it's a way of remembering that you would pick your u, so this is the u choice, not the dv choice. You're going to pick your u to be the function that comes first from this list. So I'm going to go through, and whichever one I hit first is the part of this that I likely would want as my u. Any logarithmic function would come first, followed by an inverse trig function, any algebraic functions, so think x squareds, 3x's, polynomials, trig functions, and then finally exponential functions. So let's test this out now that you're going to be picking the u's and the dv's. So in this integrand, you've got an x, which would be considered an algebraic expression, and you've got a natural log of 2x, which is a logarithmic one. So as you go through LIATE, when we hit L for LIATE, that's the logarithmic functions. So the suggestion is natural log of 2x will be our u function, okay? And our dv then is the rest of the function, which is x dx. As you go through and do your derivative for du, you're going to come up with, at first, natural log's derivative is always 1 over its quantity, but by chain rule then we need a times the derivative of that nested function dx. So as we simplify this, we're going to get 1 over x dx as our derivative for u. Working the antiderivative on the x, we're going to have 1/2 x squared. So going to plug all this in so that we can evaluate that integral, we've got our u times our v. So just in terms of writing it, I'm going to bring those out, minus. We need the integral of our v times our du. So if I can work that any better, I'm going to see if I can do that. So I've got a 1/2 times 1 over x times an x squared. I've got all sorts of stuff. So I'm just going to write it first and see what I can do to make that a simpler expression when I need to get its antiderivative. In the next few days, we're going to come across some where this amount in here is going to actually need to be evaluated again using the same types of rules. So you might come up with an integral that we need to break that integral into parts in order to evaluate. So keep working this. And again, you can always pause the video when we go through this, try it yourself, and then come back and see how you did. So the integral of x is going to end up being 1/2 x squared. So if you need to write this out at first, that half that was there, the half that comes from the integral, plus the constant sum, you might go to simplify it there right away. But make sure you're showing us enough about where this came from that we can follow your path. So there's your integral value. We'll do one more, and then you've got several in the book tonight as homework. Try this LIATE idea because you're going to be picking your own u's and dv's. So as I look through here, I see an algebraic expression, that's what that x to the third is, and I see another logarithmic one. So logarithmic always wins in LIATE, logarithmic, followed by, and then you want to sort of go down the list, the inverse trigs, the algebraic, the trig, and the exponential. So in this case, log wins the day there, and you could simplify that to 2 natural log of x. It won't be harder one way or the other here. And in this case, x cubed dx for a dv. So natural log of x squared's derivative, 1 over x squared, a little chain rule, get that 2x. dx will clean that up. So that's really going to be 2 over x dx. Okay, doing antiderivative, so we go from dv to v, we're going to end up with 1/4 x to the 4th. So again, you could pause the video, plug everything in, and come back and see how you did to evaluate that integral. Otherwise, stay with us and sort of fill everything in. So the formula says u times v, so 1/4 x to the 4th natural log of x squared. Again, you could also bring that 2 out in front, so you could also instead have 1/2 x to the 4th natural log of x. So bringing that 2 out front as a multiplier on logs is always an option. So either one of those would be okay as your beginning term. Subtract, we'll have the integral of, again, v du. So if you need to, write it first, simplify it so that you can see. So rewriting that first part, now we've got to evaluate that integral. This x is going to cancel out one factor of x. You're going to have a 1/2 as your coefficient that can come out front. And I have an x cubed sitting in there, and the antiderivative of x cubed to be 1/4 x to the 4th plus a constant. So cleaning that up and make sure you are simplifying these. Then we're going to subtract 1/8 x to the 4th and add that constant so that we have the general solution. So on your assignment tonight, you've got day 2, which comes from the book. The book is not on the online site that you've used in the past, but 7.3 is a scanned section sitting in classrooms. And you have page 350, 1-4, 9 through 10. Make sure you show the original problem, all your substitutions, and your work to simplify.